All right. So, what we had done last time, we were calculating the change in energy of an electron in an atom, taking care of the finite size of the nucleus. So, if you take that nucleus as a point charge, then if this is the nucleus point charge and you have electron around, then the potential energy is written as what, minus Z e square over 4 pi epsilon naught r. And if the finite size is taken into account, so this is this first one is when you have point nucleus, and when this finite size of nucleus is taken into account, then this is different, and this becomes what, this we had derived earlier, and this becomes minus Z e square over 8 pi epsilon naught r, and good, 3 minus r square upon r square. There are several assumptions that you must remember. The nucleus is assumed to be spherical, the nucleus is assumed to be uniformly charged in that spherical volume. So, those assumptions, simplifying assumptions we had taken, then we have derived that this is the thing. Now, if I write Hamiltonian with point nucleus, this is the Hamiltonian with point nucleus, this will be minus h cross square over 2 m del square kinetic energy operator, and then potential energy operator, that will be this. So, it is minus Z e square over 4 pi epsilon naught r. But when you take a finite size of nucleus into account, this Hamiltonian is different, and this you can write as h equal to h naught plus h 1, and that is kinetic energy operator remains the same, minus h cross square by 2 m del square, and potential energy operator is now different, it is minus Z e square 8 pi epsilon naught r 3 minus r square over capital R square. So, this h 1, which is the difference between these two, can be taken as a perturbation in the Hamiltonian, and that h 1 you can write, this h 1 is, so it is this minus this. So, Z e square over 4 pi epsilon naught r and minus Z e square over 8 pi epsilon naught capital R 3 minus r square by capital R square. Okay. So, this h 1 is simply the difference between the Hamiltonian with finite size of nucleus, which is more realistic because nucleus is indeed of finite size, and minus the Hamiltonian if I assume that the nucleus is a point nucleus. So, that is this h 1. To get the difference in energy, final energy, which comes from solving this time independent Schrodinger equation. So, the difference in energy because of this perturbation, you can write that as delta E, and that is written as your wave function, say psi naught h 1 psi naught, which is integration of this psi naught star, then h 1, and h 1 is simply multiplicative type. So, it is just multiply by that factor 4 pi epsilon naught r minus Z e square 8 pi epsilon naught capital R 3 minus r square by capital R square, and that multiplied by psi r, and that multiplied by d tau volume element. Okay. Now, since no differentiations are involved, that psi star and psi can be combined, make it psi mod square, and the what is this psi function? This is the eigen function of H naught, right. If this H1, this perturbation is small, if this perturbation is small, then you can take this wave function as the eigen function of this original Hamiltonian or unperturbed Hamiltonian, right. So, that wave function we will be writing. What is that wave function? Yeah, let us calculate the change in energy of 1s electron, which is the closest to the nucleus, and therefore, will have largest overlap with the nucleus, and therefore, the energy shift will be largest. So, if we look at 1s electron, the wave function of 1s electron, assuming a point nucleus, that can be worked out. In an atom, you have a multi electron atom, you have several electrons, and the Hamiltonian should also include in principle the terms corresponding to electron interactions, but leave that aside. You again assume that all those electrons are outside and they do not give a net electric field inside, and 1s electron is only its energy is because of the nucleus electron interaction. So, in that case you can use hydrogen like ion wave function, right. You have 1s electron which is orbiting or which is in the influence of this point nucleus having Ze positive charge, and that is it. So, if you assume that all other electrons are outside and they do not disturb much, in that case you can write this psi for 1s in point nucleus approximation. We need wave function of this Hamiltonian H naught. So, that is normalization constant 1 over pi a naught cube, right, pi a naught cube, and if it is a naught cube here, it should be z cube here. A naught and z, they always come in one combination, a naught by z. So, this is the normalization constant, and then you have e to the power minus r by a naught. So, z r by a naught, right. So, this is a hydrogen like ion, 1 electron in front of a nucleus containing Z protons and some neutrons. So, this is the wave function. So, we will use this. There are no complex part, So, taking complex conjugate is same as taking the wave function itself. So, mod square psi star psi is same as square of this. So, your delta E is integration z cube over pi a naught cube e power minus 2 times z r upon a naught, and then that factor, that whole factor, and then d tau. Now, d tau is, yes, always check dimensions. This is a volume element, it has to be length cube. One length is here, no length here, no length here, no length here. So, it has to be r square, so that it is volume. Then the sin theta d phi, this part, that integration will give you 4 pi. Okay. So, this is 4 pi r square dr. So, this integration is integration on r, and that is z cube by pi epsilon naught cube, all these things, e power minus 2 z r by a naught, and then this factor z, let me write it this way, and then 4 pi r square dr, where r should go from where to where? Limit of r limit of r goes from, this is to be integrated on whole space. So, r should go from 0 to infinity, but remember this difference of potential energy that we had calculated, potential V r, for inside the nucleus the potential is different. Outside the nucleus, even if it is a finite size nucleus assumed spherically symmetric, outside electric field and outside electric potential will be same as the potential due to point charge. Remember that if you have a spherically symmetric charge distribution, to calculate outside electric field and outside electric potential, you can take this entire thing as one single point at the center. Inside electric fields are different. So, all that difference that we have calculated, potential outside so outside potential will be same. So, that difference will be 0, right. When I am writing Hamiltonian, I wrote Hamiltonian here H naught and then H naught plus H 1. So, that H naught plus H 1 expression, in which you have all that r small r square by capital R square and all those things, that is valid for the portion inside the nucleus. For outside it is still the same. So, H 1 is for that small r less than capital R, and for r greater than capital R, what is H 1? Is 0. Is 0, because the potential with finite size and potential without finite size, they are same, correct. So, H 1 is non-zero only inside that nuclear volume, and hence the integration is to be done from 0 to capital R. And the formula that is here, this time dependent independent perturbation, that perturbation you have to take the whole space, but then here you have to write that H 1, correct, this H 1. This H 1 is 0 for r capital greater than capital R, right, and therefore, our integration is to be done only on the nuclear volume. Theta phi still go in the full range to cover that sphere, but then small r, that goes from 0 to capital R only, and hence this. Now, there is another level of approximation here. Now, look at this exponential factor. Okay, look at this exponential factor. It is e power minus 2 z r over a naught. Just try to estimate this factor. This small r goes from 0 to capital R. What is capital R? Radius of the nucleus. How much this would be typically? Femtometers, correct, few femtometers, right, few femtometers, right. So, this r, which is always smaller than capital R, has to be of this order, and a naught. What is a naught? A naught is 0.53 angstrom, that is 0.53 into 10 power minus 10 meters, right. So, this is of the order of 10 power minus 15 meters, this is of the order of 10 to the power minus 10 meters. So, this r by a naught is of the order 10 power minus 5 into z, into z. Z depends which nucleus you are taking. So, you will put some z here, but that will be less than 100 or so. Uranium is z is 92. Okay. So, this is a small number, 10 to the minus 4, 10 to the minus 3, 10 to the minus 5 type, and therefore, this factor is almost 1. E to the power 0 is 1, e to the power 0 is 1, and this is very small, 10 to the minus 4 or so, 1 by 10,000 or so. So, it is close to 0. So, this factor will be almost 1, and therefore, we will put this as 1. Okay. Then what happens? Now, let me write the whole thing again. now dictate me. This is equal to integration 0 to capital R z cube pi a naught cube. This factor I am putting 1, and what is here? Tell me. What is here? Z e square upon 4 pi epsilon small r minus z e square 8 pi capital R 3 minus and then 4 pi r square, right? 4 pi small r square dr, right? So, let us integrate. Something I can take common. So, z cube pi a naught cube, and from here what can I take? Let us take z e square over 4 pi epsilon naught. Let us take this much. Okay. Let us take this much out from this bracket, and then integration 0 to capital R. I am taking it out of the integration sign, constants. So, this I have taken out. So, it is, remember, 4 pi. So, that 4 pi also I can take out, 4 pi, and then it is only r square. So, how much is this? This I have taken, r square is coming from there. So, this will be r minus this I have taken, this 2 capital R will come from here. So, it will be r square by 2 capital R, and then this multiplied by check if this is okay. All right. So, this is z power 4 e square, z power 4 and e square, 4 pi cancels here, and then you have pi epsilon naught a square, a cube. So, pi epsilon naught and a cube. This 4 pi cancels, 1 pi remains, a naught cube remains, epsilon naught remains, z4 e square. And inside now you have integration 0 to capital R, then small r minus 3 r square by 2 capital R and plus r 4 over 2 capital R cube. This is z4 e square by pi epsilon naught a cube. R will become, after integration, r dr integration, r square by 2, and you will put the value 0 to capital R. So, this will be capital R square by 2 minus 3 by 2 r capital R here. Now, this r square will become r cube by 3. So, capital R cube by 3 plus this 1 by 2 r cube is there. So, 2 capital R cube here and r 4 r 5 by 5. So, capital R 5 here and by 5 here. Okay. Look at these first two terms, 3 cancels, capital R square by 2, same as this. So, these 2 will cancel out and you will be left with this r 5 r cube. So, it will be capital R square by 10, capital R square by 10. So, it is z to the power 4 e square divided by 10 pi epsilon naught a naught cube, this is all a naught, a naught cube and then capital R square. Okay. Are the dimensions correct? This should be energy. What we are calculating? Change in energy. So, it should be energy. Check the dimensions. Z is dimensionless. Then it is E square by 4 pi epsilon naught and R square here, A naught cube here. So, 1 by length. So, it is E square by 4 pi epsilon naught length, that type, okay, dimensionally, right. This is dimensionless. This capital R square by A naught cube, 1 by length, 1 by R, E square here, pi epsilon naught here. So, it is like dimensionally E square by 4 pi epsilon naught R, that is the potential energy expression. So, it is energy. Okay, so we have calculated the change in energy of 1s electron taking account of finite size of the nucleus. Right. If the nucleus were a point charge, then there is some 1s energy, we know the expressions. From that the actual energy is shifted this much, it is up, is going up, delta is positive, it is going up. Because of the finite size, the energy of this 1s electron has gone up by this much of amount. Capital R is the size of the nucleus, radius of the nucleus. So, that radius is coming here. If I can measure this energy difference, I can get that capital R, right, because this energy difference expression has this capital R here. This is the radius of the nucleus. So, if I can measure this delta E, I can get this capital R, but how do I measure delta E? It would have been if there is one atom with point nucleus and I measure the energy of 1s electron. There is another atom with finite size, I measure the energy and then subtract, but that is not possible. Nature has not given us atoms with point nuclei, the nuclei are extended. Okay. So, there should be a smart way of getting radius from this expression, and you know physicists are always smart, so they will find solutions how to do that. So, take this, I can remove all these things and our result is that energy of 1s electron, with finite size. Okay, so let me write this as E 1s point and plus Z 4 E square capital R square 10 pi epsilon naught A naught q. Correct. This is the 1s energy. It is more than what you would calculate with a point nucleus, and here is the difference, right. Now, look at what is called K alpha X rays. You know what is K alpha X rays? How do K alpha X rays come out? From where they are originated? They are originated again from electronic transitions. You have 1s energy level, then you have 2s energy level, then you have 2p energy level very close to this, and so on. These are the atomic energy levels. In Bohr's model or that orbit like model, if you try to picturize, you have a nucleus, then you have some electron, some, let us say this is 1s electron, right, this is 1s electron, then you will have some 2s electron at some other radius, and then you will have some 2p electron. You know why I am doing this? 2p electron, px, py, pz orbitals. See this 2p electron or any p electron or d electron, if you look at the wave function, that goes to 0 at r equal to 0. 1s electron does not go to 0. So, 1s electron has overlap with the nucleus, 2p electron will be 0 at r equal to 0. So, if you are drawing 2p, perhaps you will be drawing something like this, so that it is 0 at the center. But 2s electron will be like this, 1s electron will be like this, just picturizing, okay, some geometrical pictures. So, when this electron somehow, if there is a vacant space here, in 1s orbital you should have 2 electrons, but somehow say 1 electron is knocked out. So, there is a vacancy there. That vacancy is filled up by electrons from higher levels, right. So, if the vacancy is filled up by this 2p electron coming down here, an electron in 2p level that comes to 1s level, then some energy will be emitted, right, Hc over lambda energy, this energy minus this energy, correct. This is energy of 2p minus energy of 1s, that will be the energy. This is X-ray, this is K alpha X-ray, this photon corresponds to what we call K alpha X-ray. Now, it does not make transition from 2s because of certain selection rules. If it has to come from this so called capital L shell to this capital K shell, these are also atomic physicists call K, L, next will be M, capital M and so on. And so, if electron comes from L shell to K shell, it comes from 2p to 1s, and then the X-rays are emitted, and energies of X-rays are given by this energy difference, and these X-rays are called K alpha X-rays, right. Okay. So, let us see, if the nucleus were a point particle, what expression is there for K alpha X-ray energy, and the nucleus is finite size, what is the expression. Okay. So, the energy of K alpha X-ray is energy of this 2p state and minus energy of this 1s state. Now, as I said, 2p wave function goes to 0 at r equal to 0. So, the 2p wave function will have almost negligible overlap with the nucleus, and hence the energy calculated, energy of 2p state calculated with point nucleus or finite size nucleus should be same, right, because in 2p state the wave function is anyway going to 0. So, when you make that integration psi star h1 psi, that psi at r equal to 0, and nucleus is anyway very small, femtometers. So, that wave function itself is so small that this delta E is almost negligible. So, this you can write as just E2p, or let me write it here. This is equal to E2p, point charge, you can take it point charge, no problem. But this E1s is E1s point and then minus this delta E. Correct? Now, search for an element which has several isotopes. Isotope also you know. Isotope means capital Z remains the same, number of protons remains the same. So, it is the same element, but then the number of neutrons are different. So, I have several isotopes of an element if I have several nuclei with same Z, but somewhat different neutron number. So, that capital A will be different. These are called isotopes. So, if you look for a particular element with several isotopes and look at the energy of K alpha X-rays from all those different isotopes, what happens? So, suppose your first isotope has some mass number A naught and others are having different. For A equal to some A naught, this is the expression. Okay. So, this is the expression. Let me put R naught square here, then this is for A naught, right. This 2p state is not going to change if you are taking a different isotope. If you are taking a different isotope, what will happen? If you are taking a different isotope, then Z remains the same. Z remains the same. So, if it is a point nucleus, it just does not matter if there are 1 or 2 more neutrons or 3 more neutrons, because they are not producing electric field, electric potential. And since 2p state does not depend on the size, right, it is only the 1s whose energy is shifted up, 2p energy is not shifted up. So, for 2p it does not matter which isotope you are taking. So, this remains the same, 2p remains the same. This is anyway assuming point nucleus. So, this remains the same for all isotopes. The change is only here, because a different isotope means different size. Capital A is now different and the size is different. If the size is different, this term will be different, right. So, all these terms are same, only this term differs. So, I put a 0 here, R0 or R naught, and I put this A naught here. So, for this particular isotope, say lowest A isotope, this is the K alpha X-ray energy. And now write it for a different isotope. So, E K alpha for A. Now, this number A is different from this A naught. You can take this A naught as the lowest A in that series of isotopes. So, for any other A, this will be written as the same E2P, because this is not going to change, it is same as that, assuming point nucleus. E1s point, this is anyway point nucleus. So, it remains the same value of capital Z, and here it will be minus Z4 E square R cube, R square by 10 pi epsilon naught A naught cube. Okay. So, K alpha X-ray energies for one isotope and another isotope. So, same Z, but different values of A and therefore, different values of radius of the nucleus. So, these are the expression. Now, take difference, shift in energy, change in energy of not 1s level, not 2p level, not 2s level, shift in the X-ray energy, change in the X-ray energy, K alpha X-ray energy as you go from A naught to A, this isotope to that isotope. How much is the shift in energy? Delta E. Delta E in K alpha, which is E K alpha when your isotope is capital A, mass number is capital A, and minus E of K alpha. So, I am looking at the X-rays energies. We are going for something which is measurable. The goal was to measure the radius of the nucleus. From the experiments, I want to measure it. So, something measurable. Now, K alpha X-ray energies, it is measurable. The X-rays is coming out of that material, and those X-rays can be analyzed in certain detectors, in certain counters, their energy can be measured accurately. So, now it is a measurable quantity, experimentally measurable quantity. Now, subtract. So, it is this minus this. So, these two will cancel out and this minus that. So, it is Z 4 E square divided by 10 pi epsilon naught A naught cube and then R naught square and minus R square. Okay. So, now we do not need what would be the energy if it were point nucleus. So, that point nucleus thing has been subtracted out. But from here also we really do not know how to get that R. This expression is fine, this can be measured. So, I know how many nucleons are in the first isotope and how many nucleons are in the second isotope, that we know, that we have taken the material with this mass number and this mass number and we have gotten this quantity. So, I know the difference in the radius square, that is fine, but how that radius individually is depending on A. So, that is yet not very clear from here. What we will do is, we will assume if let us check if it goes like this. Okay. So, if R is equal to R naught A naught A cube, this is yet to be checked, If this is the case, if R can be written like this, then this delta E in K alpha will be Z 4 E square R. I have already used that symbol R naught there. I have already used that symbol R naught here. So, let me write something else. Let me put 0 here. Okay. So, that R naught square divided by 10 pi epsilon naught A naught cube, and this is now A naught to the power 2 by 3 and minus A to the power 2 by 3. Right. So, if this is true, then the relation should depend on A in this fashion, and if I measure this E K alpha for different isotopes capital A and plot that energy difference of X-rays as a function of A to the power 2 by 3, I should get a straight line. So, that is the check. If this delta E K alpha as a function of this capital A happens to be a straight line, that means this assumption is true. Okay. And if it is a straight line, then the slope is here, right. If it is a straight line, then the slope is here, and all other things are known. These are all fundamental constants. You can get this R naught. That means you will get R as a function of capital A. So, that is the trick. So, I am now going to show you on this PowerPoint slide the experimental result, the experiments that have been done with mercury isotope, mercury element. Mercury has several stable isotopes, some 7 or 8 isotopes. So, you have 7 or 8 data points for different A, what is the shift in X-ray as compared to the lowest A isotope. Okay. So, I am just going there. So, look at the screen, look at the graph at the left side. This is K, this is K X-ray isotope. Yeah. So, look at this left side, this graph. This y axis side here is the energy difference. This is all for mercury, and the lowest one is here, mercury 198, capital A equal to 198, this is the lowest. Then you have 199 here, 200, A equal to 200 here, 201 here, 202 here and 204 here. So, these are the stable isotopes of mercury. What they are plotting is negative of the change in energy. This is minus delta E, you may not be able to see on the screen. So, this is minus delta E here, and this side is a to the power 2 by 3, this side is a to the power 2 by 3, and then 198, 199, 200, 201, 202 and 204. So, these are K X-ray isotope shifts in mercury. This is taken from this reference Physical Review C17 1859, page number 1859, and the year is 1978. So, from this reference I have taken this, and in fact this figure is taken from the book of Kenneth Crane. Okay. So, this is from Kenneth Crane. Now, what do you see? Is it a straight line? Can you see this is straight line here? But you can see there are two straight lines, right? Why do you have two straight lines? One dotted line you can see, 2 points 199 and 201, they are on a different line, and that 198, 200, 202 and 204, they are on a different line. So, this is what we call even odd effect. Odd nuclei have slightly different behavior, even nuclei have slightly different behavior. So, the two odd isotopes 199 and 201, they are falling on slightly shifted, that line is slightly shifted. Although if you join these two, the slope is almost the same, right, the slope is almost the same. The even ones 198, 200, 202 and 204, they are falling on a nice straight line, they are falling on a nice straight line. Okay. Then look at the values also little bit. This point here is 0.1 electron volt, this is all in electron volt. This point here is 0.2 electron volt, this is 0.3 electron volt, this is 0.4 electron volt, and this is 0.5 electron volt. So, that also is important thing to note from this figure. Okay. So, keep this in mind. I am coming to board and I will draw it and discuss. So, what you have? You have something like this. This minus delta E was plotted here like this, and you had a straight line behavior like this, and of course, there were 2 points here. This is a to the power 2 by 3. So, this straight line thing confirms that yes, the radius of the nuclei, they follow this rule, and then from the slope you can get the value of this Cont, which is around 1.2 femtometers or so. So, that is the thing. However, the values are very small, the shift is very small, this is an electron volts, whereas the energy of the K alpha X-rays itself for mercury, it will be around 100 kilo electron volts. So, energy of K alpha for mercury isotopes will be around 100 keVs, kilo electron volts, and the shift delta E is around 0.1 electron volts. So, that means you have to measure a change of delta E by E of the order 10 to the power minus 6. Okay. So, a very small fractional change, but experiments are sensitive enough to pick up this particular change, right. Now, this situation can be improved by using what we called muonic X-rays. Have you heard of this? Muon, you know what is muon? Muon and muonic atoms. Muon is a particle of the electron family. Okay. Muon is a particle of electron family, and it has mass which is about 207 times mass of the electron, and charge same as that on electron. And there are other things, lepton number and this and that. So, there it belongs to electron family, it is like electron. It is almost like electron with a heavy mass, 207 times the mass of the electron. Not freely available, not a stable particle. They are produced in upper atmosphere because of the cosmic rays, but then these decay in something like 2 microseconds or so in their own rest frame. But these can be produced in laboratory also. You need large accelerators. You need large accelerators, nuclear reactions. Those nuclear reactions produced pions, and those pions decay to muons, and then finally muon also decays in electrons and so on, neutrino. So, in place of electron, if a muon is captured by a nucleus, what you get is muonic atoms. So, you have a nucleus, and this nucleus, instead of electron, if it catches a muon, and that muon has its own wave function and orbit and this and that, that is a muonic atom. So, it is only the mass is different, otherwise Coulomb interaction and everything is same. So, it will have 1s, 2s, 2p, all those energy levels, right, and therefore, again you will have k alpha X rays for these muonic transitions, muon going from 2p to 1s, you will have k alpha X rays. So, all this can be done with these muonic atoms. You have to produce those muonic atoms in the laboratory with accelerators, and that too for a very short time. Okay. But if you do that, there is a great benefit. And what is that? Do you remember the expression for A naught? A naught is 4 pi epsilon naught h cross square over mass times E square. Okay, that is the expression. So, this is for electron, and if it is muon, then that will be 207 times me, and so that radius decreases by a factor of 207. Okay. So, if the electron is at an average distance of some value, if it is muon, it will be 200 times closer to the nucleus, and hence the overlap with the nucleus will be much higher, because it is anyway close to the nucleus. If in fact, you can work out the values also, and for bigger nucleus like Hg or lead, these bigger nuclei, the maximum probability will be inside the nucleus itself. The nuclear size at this level, remember what will be the nuclear size radius for these heavy nuclei? Something like 6 femtometers, we worked out previous lecture, some 5, 6, 7 femtometers for these heavy nuclei, where the wave function, that psi square radial probability density maximizes. That turns out to be of the order of a femtometer or 2 femtometers or 3 femtometers. It is inside the nucleus, that means most of the time the muon is inside the nucleus. Hence that shift, hence the change in X-ray energy because of that finite size will be very high, right, and therefore observation will not be that difficult. For electronic X-rays, you have to measure 1 part in 10 to the power 6, or in absolute sense 10 to something like 0.1 electron volt in 100 keVs, whereas if you are using muonic X-rays, then since the energy shift is much higher, most of the time the muon is inside the nucleus. the effect is much higher. The shifts is of the order of kilo electron volts. Okay. So, that is the benefit. There are more methods. Isotope shifts also one can look at it. Visible spectrum. So, you have a nucleus, then you have these so called orbits, and this energy is in 100 keVs. You see 2p to 1s was 100 keV for this k alpha of mercury. For visible photon, what should be the energy? Around 100 keV is definitely X-rays. Okay. For visible photons, visible light, how much should be the energy of the photon of the order kilo electron volt or electron volt or milli electron volt? What? It is around electron volts, few electron volts. Okay. You can wavelength, you remember, for visible light what is the wavelength? Visible light, what is the wavelength range? 400 nanometer to 700 nanometers, and the energy is Hc by lambda, and Hc is 1240 electron volt nanometers. Good thing to remember, H into C is 1240 eV/nm, and lambda take something here. So, 620 nm, take 620 nm. So, this will be 2 electron volt. Okay. So, visible light photons will be around electron volts. So, you have to go for much higher transition, not n equal to 2 to n equal to 1. Even for hydrogen, n equal to 2 to n equal to 1 will be Lyman series, ultraviolet. But if there is 1s level involved in this transition, if you have some s, not 1s, some s involved here in this optical transition, then there will be some isotope shift, although very small, because 2s, 3s, 4s are farther away from the nucleus, although there is some overlap with the nucleus anyway of s electrons, but much smaller, but the effect has been measured. Alright, so that much for today. So, let me summarize what did we do today. We today elaborately discussed how do we get finite radius of the nucleus from the interaction of 1s electron with the nucleus, right. This 1s electron spends part of its time inside the nucleus, and here therefore, it experiences a different potential, and by hitting to that difference and by very cleverly manipulating to measure that difference, we could verify that radius does go as 1 by 3 r equal to some r naught a power 1 by 3, and this is something like 1.2 femtometer. However, I caution you, I am reminding you that nucleus is not a classical hardball type system. Nucleus is a quantum system, and therefore, it does not have a sharp boundary. So, when we are saying radius of the nucleus, keep that in mind. We are only giving some kind of an average radius or a typical radius. It is not a plastic ball, so that you can measure the diameter and you can measure the radius. The wave function of the nucleus itself is gradually it decreases its magnitude. Okay. You do not have a sharp boundary, you have diffused boundary, but still you can talk that okay, this is the volume in which most of the charge is there, 99% of charge is there, or 90% of charge is there, or 95% of charge is there. What we have described two methods, one electron scattering, high energy electron scattering, and then this isotope shift. They are only looking at the charges. So, essentially it is giving me the charge distribution, but then I assume that the way protons are distributed, in the same way neutrons are also distributed. So, the entire size or radius which is determined by the neutrons as well as protons, the total number of nucleons. So, that also goes in the similar fashion as the charge goes. So, that is also a assumption, but then there are methods which directly measures the mass or the mass distribution of the nucleus. Okay. It does not depend on the Coulomb interaction. There are methods where the probe is directly interacting with the nuclear forces, like alpha particle scattering. When alpha particle gets scattered from nucleus, Rutherford scattering, it is the Coulomb force which acts. But if the energy of the alpha particle is high enough, so that it goes into the nuclear range, it goes so close to the nucleus that some femtometer distance remains, then this Rutherford scattering formula, which is derived on the basis of Coulomb interaction, will fail and the experimental data will deviate. So, the energy at which this deviation starts gives you a measurement of size. So, there it is not Coulomb. When the nuclear forces start operating, and nuclear forces operates for neutron also, for proton also. So, you are directly getting into the whole mass distribution. So, all those methods are there, but at the end the final conclusion is that radius does go as capital A 1/3, and the nuclear density in most of the nucleus apart from a small surface layer is almost uniform, right. So, you have a uniform distribution of particles not only in one nucleus, across the nuclei, all the nuclei taken together. The central density is same for all those nuclei, heavier, middleweight, lightweight, central density is almost the same. And then after that surface is approached something like 2 femtometers or so, then the this nuclear density suddenly decreases. So, that is about the. So, I am trying to familiarize you with the nucleus. So, start getting pictures, start getting geometrical pictures, start getting feel of nucleus, not only in terms of wave functions and in terms of expressions, but in terms of objects. All right. So, that is for today.